Dynamic Host Configuration Protocol, DHCP. We'll talk about DHCP concepts and how it assigns the address. So we'll see how the DHCP works. So let's begin. The DHCP stands for Dynamic Host Configuration Protocol. It is a network management protocol used on IP networks. A DHCP server is used to assign an IP address and other configuration to the connected devices on the network to communicate with others. DHCP server allows the system to request IP addresses and other networking parameters automatically from the internet service providers. It reduces the network administrator's work. When the DHCP server is absent, the IP address for a computer or other devices needs to be manually assigned. But later, these devices cannot be connected outside the local subnet. So, what we learn about the DHCP, it can be implemented on home networks, to wide area networks, and region ISP networks. Most of the home networks receive a globally unique ID within the ISP, Internet Service Provider networks. For the local ISPs, for the local networks, DHCP assigns a local IP address to every connected devices within a network. We can also use the router as a DHCP server. There are millions of devices in the world, and each individual device needs a unique IP address. For the TCP IP protocol supports a built-in DHCP protocol, so it automatically assigns a unique IP address to each connected device and keeps tabs of them. Almost all IP addresses are dynamic. The DHCP port from the server, it is a server of 67, and for the client is 68. It is a client server protocol that uses UDP services. An IP address is assigned from a pool of addresses. In DHCP, the client and the server exchange mainly for DHCP messages in order to make a connection, also called the DORA process, DORA. We'll learn about the DORA process in next video, so we'll explain how it works. So, for example, here we'll learn it is a DORA process that make a connection. So, but there are 8 DHCP messages in the process. So we'll talk about the 8 messages later on. We'll know DHCP is based on client-server model, and it is based on discovery, offer, request, and acknowledgement. So why we use DHCP? So we'll learn about like why we are using DHCP in this era. DHCP helps in managing the entire process automatically and centrally. DHCP helps in maintaining a unique IP address for host using the server. DHCP servers maintain information on TCP IP configuration and provide configuration of address to DHCP enabled client in the form of lease offer. So component of DHCP. There are main components of DHCP that will include below. So DHCP server is basically a server that holds IP addresses and other information related to configuration. DHCP client, it is basically a device that requires configuration information from the server. It can be a mobile, laptop, computer, or any other electronic device that requires a connection. DHCP relay. DHCP relays basically work as a communication channel between DHCP client and server. IP address pool. It is a pool or container of IP addresses possessed by the DHCP server. It has a range of addresses that can be allocated to devices. Subnets. Subnets are a smaller portion of the IP networks partitioned to keep network under control. Subnet is a broader chapter. It is a wide. So we'll talk about subnets, how it works, how it assigns, how it includes all the IP addresses, how we assign the ranges. So we'll talk about later, explain and elaborate so that you can understand the subnet concept. So let's begin in the DHCP. Lease, it is simply the time that how long the information received from the server is valid. In case of expiration of the lease, the tenant must have to reassign the lease. DNS servers. DHCP server can also provide DNS domain name system server information to DHCP client, allowing them to resolve domain name to IP addresses. Default gateway. DHCP server can also provide information about the default gateway, which is the device that packets are sent to when the destination is outside the local network. Options. DHCP server can provide additional configuration options to clients, such as the subnet mask, domain name, and time server information. Renewal: DHCP client can request to renew their lease before it expires to ensure that they continue to have a valid IP address and configuration information. Failover: DHCP servers can be configured for failover, where two servers work together to provide redundancy and ensures that client can always obtain an IP address and configuration information even if one server goes down. Dynamic updates: DHCP server can also be configured to dynamically update DNS records within the IP address of DHCP clients, allowing for easier management of network resources. Audit logging: DHCP server can keep audit logs of all DHCP transactions, providing administrators with visibility into which devices are using with IP addresses and when leases are being assigned or renewed. Format. So we'll talk about and explain how the format works, the DHCP format. First, hardware length. This is an 8-bit field defining the length of the physical address in bytes. For example, for Ethernet value is 6. 2. Hop count. This is a 8-bit field defining the maximum number of hops the packet can travel. Transaction ID. This is a 4-byte field carrying an integer. The transaction identification is set by the client and is used to match a reply with the request. The server returns the same value in its reply. Number of seconds. This is a 16-bit field that indicates the number of seconds elapsed since the time the client started to boot. Flag. This is a 16-bit field in which only the leftmost bit is used and the rest of the bit should be set to zeros. A leftmost bit specifies a forced broadcast reply from the server. If the reply were to be unicast to the client, the destination IP address of the IP packet is the address assigned to the client. Client IP address. This is a 4-byte field that contains the client IP address. If the client doesn't have this information, this field has a value of 0. Your IP address. This is a 4-byte field that contains the client IP address. It is a field by the server at the request of the client. Server IP address. This is a 4-byte field containing the server IP address. It is a field by the server in a reply message. Gateway IP address. This is a 4-byte field containing the IP address of a router. It is filled by the server in a reply message. Client hardware address. This is a physical device, physical address of the client. Although the server can retrieve this address from the frame sent by the client, it is a more efficient if the address is supplied explicitly by the client in the request message. Server name. This is a 64-byte field that is optionally filled by the server in a reply packet. It contains a null terminated string consisting of the domain name of the server. If the server doesn't want to fill this data, so the server must fill it with all zeros. 12 boot file name. This is a 128-byte field that can be optionally filled by the server in a reply packet. It contains a null terminated string consisting of the full path name of the boot file. The client can use this path to retrieve other booting information. If the server doesn't want to fill this data, the server must fill it with all zeros. Options. This is a 64-byte field with a dual purpose. It can carry either additional information or specific vendor information or additional information. The field is used only in a reply message. The server uses a number called a magic cookie in this format of an IP address with a value of 99.130.83.99. When the client finishes reading the message, it looks for the magic cookies. If present, the next 60 byte are options. The 8 DHCP messages. There are DHCP messages, how it cover and how it send the data, how it acknowledging the data. So we'll talk about the 8 DHCP messages, how it covers. DHCP discover messages. First, this is the first message generated in the communication process between the server and the client. This message is generated by the client host in order to discover if there is any DHCP server or servers are present in a network or not. This message is broadcasted to all devices present in a network to find out the DHCP server. This message is 342 or 576 bytes long. As shown in the figure, the source MAC address client PC is 0800-2B2E AF2A. The destination MAC address server is 12 times Fs. The source IP address is 0.0.0.0 because the PC had no IP address till now. And the destination IP address is 255.255.255.255, IP address used for broadcasting. As they discover messages in broadcast to find out the DHCP server or servers in the network. Therefore, broadcast IP address and the MAC address is used. DHCP offer messages. The server will respond to the host in the message specifying the unleased IP address and the other TCP configuration informations. This message is broadcasted by the server. The size of the message is 342 bytes. If there is more than one DHCP server presence in the network, then the client host will accept the first DHCP offer message it receives. Also, a server ID is specified in the packet in order to identify the server. Now, the offer message, the source IP address is 172.16.32.12, server's IP address in this example. The destination IP address is 255.255.255.255, broadcast IP address. The source MAC address is 00AA00122345 and the destination MAC address is 12 times F. Here, the offer message is broadcast by the DHCP server. Therefore, destination IP address in the broadcast IP address and the destination MAC address is 12 times F. And the source IP address is the server IP address. And the MAC address is the server MAC address. Also, the server has provided the offer IP address 192.168.32.51 and a release time of 72 hours. After this time, the entry of the host will be erased from the server automatically. Also, the client identifier is the PC MAC address 0800-2B2E-AF2A for all the messages. DHCP request message. When a client receives an offer message, it responds by broadcasting a DHCP request message. The client will produce a gratuitous ARP in order to find out if there is any other host present in the network with the same IP address. If there is no reply from another host, then there is no host with the same TCP configuration in the network, and the message is broadcasted to the server, showing the acceptance of the IP address as the client is also added to this message. Now, the request message is broadcasted by the client PC. Therefore, source IP address is 0.0.0.0 as the client has no IP right now. And the destination IP address is 255.255.255.255, the broadcast IP address. And the source MAC address is 0800-2B2E AF2A, PC MAC address. And destination MAC address is 12 times F. Note, this message is broadcasted after the ARP request broadcast by the PC to find out whether any other host is not using the offered IP. If there is no reply, then the client host broadcast the DHCP request message for the server showing the acceptance of the IP address and other TCP configuration. 4. DHCP acknowledgement message. In response to the request message received, the server will make an entry with a specified client ID and bind the IP address offered with the lease time. Now, the client will have the IP address provided by the server. Now, the server will make an entry of the client host with the offered IP address and lease time. The IP address will not be provided by the server to any other host. The destination MAC address is 12 times F and the destination IP address is 255.255.255.255 and the source IP address is 172.16.32.12 and the source MAC address is AA00123456 server MAC address. Now we'll talk about DHCP negative acknowledgement passage, NAC. Whenever, a TCP server receives a request for an IP address that is invalid according to the scopes that are configured, it sends a DHCP NAC messages to the client. For example, when the server has no IP address unused or the pool entry is empty, then this message is sent by the server to the client. DHCP decline. If the DHCP client determines the offered configuration parameters are different or invalid, it sends a DHCP decline message to the server. When there is no reply to the gratuitous ARP by any host to the client sends a DHCP decline message to the server showing the offered IP address is already in use. DHCP released DHCP release. Our DHCP client sends a DHCP release packet to the server to release the IP address and cancel any remaining lease time. DHCP inform. If a client address has obtained an IP address manually, then the client uses DHCP information to obtain other local configuration parameters, such as domain name. In reply to the DHCP information message, the DHCP server generates a DHCP acknowledgement message with the local configuration suitable for the client without allocating a new IP address. This DHCP acknowledgement message is unicast to the client. All the messages can be unicast also by the DHCP relay agent if the server is present in a different network. So we'll talk about advantages of DHCP. So DHCP advantages includes centralized management of IP addresses, centralized and automated TCP IP configuration, ease of adding new clients to the network, reuse of IP addresses that reduces the total number of IP addresses that are required. The efficient handling of IP addresses changes for clients that must be updated frequently, such as those for portable devices that move different locations on a wireless network. Simple reconfiguration of the IP address space on the DHCP server without needing to reconfigure each client. The DHCP protocol gives the network administrator a method to configure the network from a centralized area. With the help of DHCP, easy handling of new users and the reuse of IP addresses can be achieved. Disadvantages of DHCP. We'll talk about DHCP disadvantages that includes IP conflict can occur. The problem of a DHCP is that clients accept any server accordingly when another server is in the vicinity, and the client may connect with the server, and the server may possibly send invalid data to the client. The client is not able to send the network in absence of a DHCP server. The name of a machine will not be changed in a case when a new IP address is assigned. So we'll explain more about DNS, how DNS works. The process of DNS resolution involves converting a host name, such as www.example.com, into a computer-friendly IP address, such as a 192.168.1.1. An IP address is given to each device on the internet, and that address is necessary to find the appropriate internet device, like a street address is used to find a particular home. When a user wants to load a web page, a translation must occur between what a user types into a web browser, example.com, and the machine-friendly address necessary to locate the example.com web page. In order to understand the process behind the DNS resolution, it is important to learn about the different hardware components a DNS query must pass between. For the web browser, the DNS lookup occurs. Behind the scenes, that requires no interaction from the user's computer apart from the initial request. There are eight steps in the lookup, DNS lookup. A user types example.com into a browser, and the query travels into the internet and is received by a DNS recursive resolver. The resolver then queries a DNS root name server. The root name server then responds to the resolver with the address of a top level domain TLD DNS server such as .com, .net, etc., which stores the information for its domain. When searching for example .com, our request is pointed towards the .com TLD. The resolver then makes a request to the .com TLD. The TLD server then responds with the IP address of the domain's name server. For example, .com, right? Lastly, the recursive resolver sends a query to the domain names server. The IP address for example.com is then returned to the resolver from the name server. The DNS resolver then responds to the web browser with the IP address of the domain requested initially. Once the eight steps of the DNS lookup have returned the IP address for example.com, the browser is able to make the request for the web page. The browser makes a HTTP request to the IP address. The server at that IP returns the web page to be rendered in the browser, like the picture. What is a DNS resolver? So the DNS resolver is the first stop in the DNS lookup, and it is responsible for the dealing with the client and made the initial request. The resolver starts the sequence of queries that ultimately leads to the URL being translated into the necessary IP address. A typical uncached DNS lookup will involve both recursive and iterative queries. It is important to differentiate between a recursive DNS query and a recursive DNS resolver. The query refers to the request made to a DNS resolver requiring the resolution of the query. A DNS recursive resolver is the computer that accepts a recursive query and processes the response by making the necessary request. So, what is DNS cache and how it caching? So, where does the DNS cache occur? So, we'll talk about more. The purpose of caching is temporarily store data in a location that results in improvements in performance and reliability for data request. DNS caching involves storing data closer to the requesting client so that the server DNS query can be resolved earlier, and additional queries further down the DNS lookup chain can be avoided, thereby improving load times and reducing bandwidth CPU consumption. DNS data can be cached in a variety of locations, each of which will store DNS records for a set of amount of time determined by a time to live (TTL). Browser DNS caching. Modern web browsers are designed by default to cache DNS records for a set amount of time. The purpose here is obvious. The closer the DNS caching occurs to the web browser, the fewer processing steps must be taken in order to check the cache and make the correct request to an IP address. When a request is made for a DNS records, the browser cache is the first location checked for the requested record. In Chrome, you can see the status of your DNS cached by going to Chrome colon double forward slash net hyphen internals hyphens hashtag DNS. There are four DNS servers involved in loading a web page. DNS recursor. The recursor can be thought of as a librarian who is asked to go find a particular book somewhere in a library. The DNS recursor is a server designed to receive queries from a client machines through applications such as a web browser. Typically, the recursor is then responsible for making additional requests in order to satisfy the client's DNS query. Root name server. The root name server is the first step in translating or resolving the DNS IP address in domain name system. So it is the first step it is the first step in translating or resolving human readable host name into IP address. It can be thought of like an index in a library that points to different racks of books. Typically, it serves as a reference to other more specific locations. TLD name servers. The top level domain servers, TLD, can be thought of as a specific rack of books in a library. This name server is the next step in the search for a specific IP address, and it hosts the last portion of a host name. In example.com, the TLD server is .com. Authoritative name server, authoritative name server. The final name server can be thought of as a dictionary on the rack of books, in which a specific name can be translated into its definition. The authoritative name server is the last stop in the name server query. If the authoritative name server has access to the requested record, it will return the IP address for the requested host name back to the DNS recursor, the librarian. That means the initial request. So, what is the difference between authoritative DNS server and the recursive DNS resolver? Both concepts refer to the servers, group of servers that are integral to the DNS infrastructure, but each performs a different role and lives in different locations inside the pipeline of DNS query. One way to think about the difference is the recursive resolver is at the beginning of DNS query and the authoritative name server is at the end. DNS server not responding. So what does that mean? If DNS server is not responding, you may get a message that says DNS server isn't responding. After entering a domain name in the URL bar of a browser, this means there was an attempt to communicate with the DNS server, but the server failed to return a result. This could be due to a few different things. Your internet connection is weak or unstable, making it hard for your browser to communicate with the DNS server. Your DNS setting or browser need to be updated. There is an issue with the DNS server, such as a loss of power at the data center where it is housed. So, as we have talked about the DNS lookup, so how to perform a DNS lookup? Each domain name has a DNS record, and there are pulled by and these are pulled by name servers. You can check the status of a DNS records associated with your domain. You can also examine the name servers to ascertain which records are being pulled by the servers. On a Windows computer, for example, this is done using the ns lookup command. Here is how to do it. Access to Windows command prompt by going to start command prompt. You can also get it to via run cmd. Type ns lookup and then hit enter. The default server gets set to your local DNS. You then set the type of DNS record want to look up by typing set type equals hash hash hash, where hash hash is the record type. Then hit enter. You can also use a 4 times a or a plus 4 times a, any CNAME, MX, NS, PTR, SOA or SRV as the record type. Enter the domain name you want to query. Hit enter. At this point, the NS lookup returns the record entries for the domain name you have entered.